Okay, so Ava's want to know when did I decide this is what I wanted to do. I was starting to type that, but that could take a while. So that's been sort of a not a very linear path. I always liked to draw since I was little. Always into the arts. My father was an architect, so I had access to AutoCAD at a fairly young age. I think I was 10 years old when he brought the first computer home with AutoCAD on it. So I started playing around with that. I think that was released 12. It was 93. Um, Immediately fell in love with that. Just being able to draw on the computer was kind of fascinating. So I guess I kind of decided that path at a young age. One of his employees introduced me to Rhinoceros 3D. I was in beta release, I think, in 1996. So I started playing around with 3D modeling. That wasn't long after the first Jurassic Park came out. They had this amazing T-Rex scene. That was like really cool. I was like, oh, I got to do 3D. So once I got into college, fast forward a few years, I decided that I was going to be a computer animator, and I started learning Maya. And one of the other professors at the university convinced me to switch majors when I was almost done with that to metalworking and jewelry. He's actually one of the a colleague of mine now. We both work at James Avery, but he was using Rhinoceros 3D as well. And since I had prior experience to that, I kind of stuck with that, and that ultimately led into what I'm doing today, sort of product development using 3D CAD. There's just kind of a roundabout way of getting there. So I didn't know that this is what I wanted to do. I knew that I wanted to be involved with aesthetics and engineering and problem solving, whether it's in a visual nature or a structural or mechanical nature. I just I like the challenge. I like having something functional that also had to look nice. So yeah, I just kind of fell into it. Just stayed on the path of I knew I wanted to design something, and I knew I liked creating things, and that kind of happened at a fairly young age. So I don't know if I ever fell on this is exactly what I wanted to do, but it's just sort of where my path led me. Hope that wasn't too much of an answer, but there you go.
And how do you combine, for example, a design with manufacturer requirements? Because there's kind of like design artists and then design manufacturer that you have to stick with some requirements or you have some limitations to your design.
Oh yeah, so that's a really good distinction, especially with the role that you and I fill at James Avery. They're very much a design-oriented company, so our conceptual designers are the ones that work with the marketing team, and they try and decide, what trends and what formats are we going to try and pursue for our aesthetic designs, and they're not really hindered by the manufacturing process, which is a good thing because in the end you want the design aesthetic to come through. It's paramount to the end result. So you start with the bullseye as your target. So we don't inhibit their process at all. Whatever they want to use is available to them. At that point, once a prototype is landed and the design team and marketing all agree that this is what we want to move forward with, then it comes to Monica and I's department and product development. And that's where we try and iron out some of these details that are going to be a little bit difficult to mass produce. It's always easier to produce one item. It's so much more difficult to consistently produce thousands of them. And that's sort of where the role of a product specialist like Elbjorn or a technical designer like myself, that's where we come into play and try and support that and ensure that the aesthetics are maintained no matter how many of these we produce.
Cool, thank you.
Yeah. And just to add, that's not the only way that works. I've been part of other companies and firms where their intent was to create what they defined as a fully defined or a well-rounded designer. And I think that's more along the terms of where the industry is going to go in the future, where the technical aspect and the CAD aspect are going to be part of the design process up front. Yeah, one of the companies I worked for, they were unsuccessful simply because of capacity needs. They couldn't keep up with this, but their goal was to have someone who could do trend analysis, forecast the results, does conceptualize the piece, and then technically design the piece for manufacturing. So that would all be one team of people. That's highly specialized skills to have in one person. It's very, very difficult to achieve. But it's it's part of what some people have a goal for. But like I said, that's not really how it works today. It's just the amount of product that people need to produce to stay relevant for a large scale manufacturer. You usually separate the two. You'll have your conceptual designers that are only worried about the aesthetic, uh, paying attention to scale and proportions, obviously, but they're not really concerned with the technical or mechanical aspect of mass producing these items.
Hmm. So then, will you recommend? Well, not recommend, but as you were saying, like there's a conceptual designer and there's a technical designer and there's a, I guess, other designers. So, so how do you know where do you like if you want to be a technical designer or just a designer? Because whenever I say, "Oh, I just want to be a designer," you kind of like don't take that in consideration. It's just, oh, I just want to design things.
Yeah, no, that's a really really good point. Like speaking back to
So
when
wait. So will you recommend becoming an expert or I don't know? Now answer.
or becoming an expert in what
I don't know on the things that you like.
I would say, approach it the same way you'd approach like if you're going to write a research paper, right? You'd have an outline, okay?
Mhm.
Or if you're going to develop a product, it's the same thing. You start with the end in mind. What is your goal? Well, you say, okay, I love to draw. I want to be around aesthetically pleasing images or products. Yeah, I care about the way things look. That's part of what I enjoy doing. If I didn't have anything else to do, would I sit down and try and draw something I see, or draw something from my mind, draw cartoons, or draw an object, or anything like that, or maybe sculpt something from some clay or something like that. I've met plenty of people that in college, you meet like-minded people that we all had similar stories like that. When we were young, we always like to do some sort of craft or art or something. So if you can identify that, you say, okay, I want to be a designer. Perfect. That's your end goal. Now you have to go and define, to your point, what kind of designer do you want to be? That's a very broad topic. So there's a lot of research. So you could be conceptual or technical designer. It's a very small drop in a very small bucket because we're talking about product development. You could be a conceptual designer for movies or video games or theater, or you could be a
Right.
set designer. You could be a landscape architect. I mean, it's a really long list of professions that you could pursue. Um, I would say that let that sort of define along the way as you research these roles and you understand
Yeah.
what's entailed. That you'll kind of know what feels right. Um, and one of my past experience, I've tried to do the conceptual designer. I thought that would be totally what I wanted to do. Um, but as I tried to fit more in that role, it didn't really feel right. It felt forced. From a design standpoint, um, I was a jewelry and metals major in college, but I focused much more on ornamental ironwork, blacksmithing, fabrication, that sort of thing. And while I was still honing my skills and understanding the principles and elements of design and how to implement those, um, it didn't exactly translate into fine metalworking. I think a fashion background would have been much more beneficial if I knew I was going to be a conceptual jewelry designer.
Mm.
Understanding the materials and the process didn't help me as much as understanding the industry that that type of object fits in. Um, but on the same token, understanding the materials and the process definitely helped me become a technical designer from that standpoint. So I understand what's important to the conceptual designer, um, what is visually necessary to remain, and where we can maybe adjust without sacrificing the aesthetic to appease the materials and the process and the manufacturing side of things. So I think I always like having a hands-on approach on things and building things. So I think that's sort of my own path of how I fell into a technical designer role. I didn't follow fashion trends. I didn't exactly keep up with, what was a Pantone color of the year and how's that
Mm.
going to affect the jewelry market. I had experience with all those things, but it wasn't it wasn't a good fit. It felt, like I said, it felt forced. And so I just naturally fell more and more into a technical designer role. And I just enjoyed it more. It was the type of problem solving that I wanted to do. So I think everyone will end up finding their own path.
Yeah.
Um, Another thing to consider is the type of role that you're going for. It's more of a practical reflection on it, but you could think of it this way in terms of, how important is it for you to be a conceptual designer? They get a lot of the recognition, as they should. It is their ideations that we're, their IC, their intellectual property that we're putting out there.
Hmm.
So a lot of recognition does go to that, and it is very rewarding. And a lot of people want to do that position, but on the same side of the coin is that you have to worry about the amount of competition you have when you apply for a job. So there's also that, like, technical designers often are behind the scenes. It's not a whole lot of glory with it, and which is fine for some people. Definitely for me, I don't mind it. I still get to enjoy my work, and like I said, it's not my intellectual property that we're executing, so I don't have any ownership over the design. Um, but at the same time, there's not a lot of people that have the skill sets for that job either that are in this industry. It's an easier role to find a job doing than it is a conceptual designer, because everyone wants to be a conceptual designer.
Mm. Let's see.
I hope that translated well. But
Yeah. And like, I don't know if you remember our friend Nick, that he wanted to be a designer, but then he realized that he wasn't good at, he struggled too much with kind of like having a design. And so he, now right now he's in quality, because quality, it's exactly like the tolerances that he was talking about and all that. So yeah, it's it's I guess, sorry, we took too long. Let's get started. Let me
yeah.
share two videos, like 2-minute videos, and then here. Okay, are you guys able to see my screen?
We're trying to do something that's never been done before. Something that seemed impossible.
We are constantly trying to push our designs just a little bit further. I'm always saying, make it even better. Before I had Fusion 360, the question was, can I really make that? Now it's more like, what can't I make?
Now I have a simple way to solve really complicated problems.
Starting a project used to be so daunting. We'd spend days trying to make a prototype. I love how intuitive the software feels. It's like an extension of my brain.
Our team is really tight-knit, even though we have people all over the world. Fusion 360 keeps us connected.
I'm able to spend more time with the things that matter to me most, because I can get my work done anytime, anywhere. It's an amazing feeling to hold something you've brought from idea to reality.
With Fusion 360, I don't have to compromise between cost or quality.
I'm an engineer.
I'm a machinist.
I'm a designer, and I use Fusion 360.
Fusion 360. One product, unlimited possibilities.
This one.
Yeah, my name is Aaron Magnan. This is Fusion 360. What does good design look like to me?
So real quick,
Good design should have a very positive impact.
It's what makes us better.
We have been doing good design. We want to raise the level of design to what has not been possible before. The challenge with the way design has been done so far is that it's limited by outdated rules and assumptions, the designer's past experience, and our imagination.
The product designer wants the best possible design solution while not jeopardizing cost.
The risk we run in that resource-constrained environment is that we don't explore as deeply or as richly as we might want to.
We all benefit from good design.
Generative design creates the opportunity for us to ensure that we're diving deep and that we're understanding all the available ideas that might lie before us.
Because the limitations are gone, the handcuffs are off. It's providing me solutions, but not just one solution, a whole multitude of solutions.
Generative design has the ability to produce a solution that previously could not be conceived.
By integrating artificial intelligence, we can for the first time use the term CAD in its true meaning, having the computer as a partner in the design process.
You're not concentrating on mastering a tool any longer, you're just mastering the problem and you're letting the computer do all the work.
Imagine being able to design the perfect solution every time.
Being able to design without fear of what you didn't come up with.
Imagine being able to design with augmented intelligence.
Create products, buildings, and cities that are intelligent, with a fraction of budget and time.
At the speed of creativity.
And without limitations.
Cool.
Very cool.
Okay. Very cool. Okay, so how do we want to do this? Let me just let you talk.
All right. Well, I guess we'll just go ahead and jump right into it. So before the end of the presentation, I'll go ahead and share some of the providers of software if any of y'all are really interested in 3D CAD and going that route. What I'm going to focus on today is two packages. The first one is by Autodesk, who's one of the companies I'll share with you at the end. They make Fusion 360. There's a video you just saw. And other software I'm going to focus on, if there's time and if there's interest from y'all, is called Blender. The reason I'm focusing on these two softwares is because they're completely free to use, even for professional use. And I really wanted to focus on that because one of the huge obstacles that we had back in the day was trying to get access to software. So you try to get pirated copies or bootleg someone else's copy or something like that. Anything you do to get your hands on software, because it was still kind of expensive and getting the system to run it wasn't cheap either. But nowadays, you can get a really good computer for $700 and free software and you're good to go. You could probably get by on less hardware than that. But anyway, so I'm going to focus on Fusion 360 first because that's directly related to product development. But as the video said, this is just a tool. Just for any of y'all who are interested in going to any level of design work, whether it's conceptual, technical designer, mechanical designer, anything like that, you first and foremost need to understand and master the principles and elements of design and your 2D drafting and or sketching and drawing capabilities. I just want to make sure we start off with that on the right foot. These CAD softwares are not going to make you a better designer. They're just a tool. So if you want to get in the design field, study the fundamentals first. Once you fundamentally understand those, you'll just be able to execute those things faster using the new tool. I see a lot of people focus on hardware and the new software and the new updates, and it's irrelevant. You got to focus on the fundamentals. Once you have that down pat, you'll excel a lot faster once you get into the 3D space. So with all that being said, I'm going to share screens and we'll dive right in. Feel free to type in questions as we're going. And yeah, let's get going. Enough time wasted, I guess. Let's see. All right. I'm guessing y'all can see my screen okay?
Yeah.
All right. Just let me resize the window real quick. Okay, Monica, you shared a picture of the part with them that we're building today?
Yes.
Okay.
Can you see me?
I think I still got the screen share.
Okay. So do you remember a little toy that we had? I thought it was pretty cool to have it draw it. And then we had a friend that 3D printed it for us. So, and then David also did this drawing. So this is, I guess, what you were talking about, the basics. Kind of like understand how this part is made. So
Yes,
like
those are basic drafting fundamentals, projected views, how you get isometric, dimetric, or trimetric views, 1, 2-point, 3-point perspective. All of those things are very important. Unfortunately, I apologize to y'all. This is not the best example, but you get the idea. The point is focus on principles and elements of design. I can post a link to those if y'all are interested, as well as your hand skills. If you cannot draw a line on paper, you cannot draw a line on a computer. So just keep that in mind. Enough of harping on that. We're going to start sketching. So Fusion 360 is sort of a unique package. It's a jack of all trades to speak, meaning that it can do solid modeling, surface modeling, sheet metal, and there's some mesh and subdivision tools in there as well. For now, I'm going to focus on the solid modeling aspects. These are meant to extrude fairly simple shapes. You can make things look very complex, but they're all generally composed of fairly simple geometry. But I'll kind of show you how some of that works as we go. In a solid modeler, you, as with any 3D CAD, you always start with a sketch. I hesitate to say two-dimensional because while most sketches are created on a two-dimensional plane, you can have what they call 3D sketches.
Are you sharing your screen?
Oh, I thought I must have stopped sharing it. Sorry.
There we go.
Sorry about that, y'all. Yeah. Technical designers having technical issues. There you go. So what we're gonna do is we're gonna pick one of these planes to sketch on. Sorry, we have a little gimbal in the top right here to manipulate and rotate around the space. You have X, Y, and Z planes. This is what we call the top plane, so we're gonna go ahead and sketch on that top plane. I'm gonna set my view to line up with that view. And then you have a series of different types of curves. You can draw a line. It's a simple polyline. As I'm drawing it, you can see that it's giving me a readout for the length and the angle of the line. We'll be able to actually control that as well. And I don't know if you can see the little icons that are popping up next to the line. It's like little light blue symbols. Can y'all see those?
Mm-hmm.
These are known as constraints. Most parametric software packages use these. These help define the line. Aside from the angle or the length of it, if you look at the two light blue slash symbols there, this is telling you that if I snap the line there, it's going to make that line parallel to the line beneath it because that line beneath it also has the two slash marks. So this is a way that I can control that line and say, listen, I might want to change the length of you, but I want you to always be parallel with the line beneath you for some reason, if we're defining a part a specific way. Or I can tell it with this symbol that I always want you to be vertical relative to the sketch plane. Let's see, there's another one that popped up. Yeah, this is perpendicular to the reference line at the very bottom. So this line right here, if I sit here, it's perpendicular to that. That's what the little square symbol means. So all these things help kind of quickly define the line. And the reason this is important is because this allows us to change the line as we go, and we can define this with actual dimensions. So I'm going to go ahead and hotkey this right quick, but the actual icons for it here, and we can dimension this now. And you say, okay, from this point to this point, we'll say that's 0.75 inches. And it scaled the rest of the drawing because we've only defined one dimension, but just kind of showing you how some of this works. We can pick two lines, it'll automatically define an angle. So you say this is 60 degrees. But if you'll notice that even though I have it defined 60 degrees, I want this to be horizontal to my construction plane to make them flat. So I'll click the horizontal vertical. The way this works is it'll make it horizontal or vertical depending on whichever one the line is close to. So this is another type of constraint. So now it shifted everything. As I'm defining this, we'll see that the color of the line hasn't changed. It's still this light blue color with most CAD packages that are parametric, meaning like Fusion or SolidWorks, something like that. The color of the line will not change if it's not completely defined. And I'll kind of get into what exactly that means in a second, but just be something to be aware of, that we can still move this around and it's still a light blue color, which means that if we were to change a part later on, not everything is completely defined. So it might break whatever geometry we're going to create. So we always want to make sure we have a fully defined curve or sketch before we start making 3D geometry. So I'll just keep dimensioning here. I'm not actually making any specific part right now. I'm just kind of showing y'all the process of how to fully define a curve or a line. Okay, so I'm adjusting the angle of this, but let's say I want this to be perpendicular. So I will go ahead in my constraints. I'll find the icon that says perpendicular. And I will click this line and that. So now this line will always be perpendicular to this line. So if I change this angle now, you can see the angle of this change as well.
Whenever you start a design, you always start on your, like by paper and pen, or you think it's easier to start just on the computer and just jump in?
I think to varying degrees, it's always better to start with paper. Nothing will conceptualize an idea faster than your hands and eyes and thoughts on a piece of paper. You can make notes, you can do thumbnail sketches much faster than you can draw lines in here, because you're trying to approach it from a very technical mindset. It's not open and fluid enough. So yeah, even if it's just little thumbnail sketches, like little small notes that you're kind of taking as you go, yeah, sketches are always better place to start.
So like this one will give you like an understanding of where you're gonna start.
That one, I wouldn't necessarily take it that far on paper all the time. I think a good conceptual designer will provide a technical drawing like that for a technical designer to follow when they're doing CAD work. But the conceptual designer is not going to go through the trouble of making that level of drawing until they've finalized which idea they're going to follow through with. So what I was referring to is more like what you would present at like a design review, where you might have 25 to 30 thumbnail sketches of different ideas that kind of fit within a defined format. So if you're going to design an engagement ring that's going to be a solitaire, then you're going to go ahead and sketch 25 different versions of a solitaire ring that fit within a certain design format. So if they say, you know, a lot of the vintage jewelry, like Edwardian jewelry, is coming back for some reason with rose cut stones. Well, you're going to go and draw 25 different versions of that that are different than everyone else ever did.
Or like the door that you guys designed, that you guys, I share with them like the sketches and.
Yeah, absolutely. Absolutely. That's part of it. That's more of a raw part of the development process. You'll start with a sketch, and then you'll take sheets of vellum and you'll sketch over your previous sketches to kind of define your various iterations. But even that's even further earlier in the process, where you haven't really settled on your own design sensibilities yet. So you're kind of working through different ideas that are coming through you. You're trying to work as fast as you can to develop those ideas, but it's not even something you would present at design review. At that point, you might have 60 different sketches. And of those 60 sketches, you'll cull that down and you'll make little thumbnail sketches, 1 to 2 inch squares, right?
Mm-hmm.
Very, very small sketches. And you'll have all of those represented on a piece of paper. And that's not to say you drew them 1 to 2 inches. That's just, you might do a quick sketch of different ideations that you like, that you want to present a design review, and you would scale them down to fit on a sheet of paper, because design review isn't composed strictly of designers. It's people who are aesthetically minded, but they also have a business mindset. So a thumbnail sketch is enough to suffice for getting the idea or the aesthetic across that you want to pursue for the rest of the design. And then from that, they might select anywhere 1 to 5 of those thumbnails and say, we're going to pursue further. And that might even get called along the process. Maybe you tried to push the envelope for manufacturing. And so out of those, say they picked 4, 2 or 3 of those might not make it. You might know just one design that goes all the way through to manufacturing and through the catalog. So yeah, sketching is really important, especially if you're going to be a conceptual designer. It's absolutely essential. You're not going to be a conceptual designer if you're not doing sketches. That's your primary tool. The CAD is secondary, very limited in usefulness.
Very good advice.
Sorry, so let's go ahead and see. So I know that this this curve is not fully defined yet because it's still blue. This line is fully defined. That's black line, so we know that that's good. So what I usually do is kind of move the curve around. I can see that I'm dragging my mouse everywhere. The cursor's moving, but the only thing that's shifting is side to side. So I'll go ahead and put a dimension line on this. And now it's locked that in place. So it's fully defined curve. This is good. So if I control this and something else moves around, I know down the road it won't break my model. Like I said, apologies, this isn't really relevant to what we're going to build. I just want to get y'all to understand the concept of a fully defined sketch. So, and how to use constraints and dimensions, just get you aware of the concept. We're going to be building something much simpler. So I'm going to start with a rectangle. Start with the center point, go out. Very good. Now, when you use these predefined tools, you can see they come in with their own constraints. This line has the equal symbol and the parallel symbol. So we know this is always horizontal. This is always perpendicular. So they've predefined the constraints to draw a rectangle. All we have to do is set up some dimensions. There's only a rectangle tool. There's not a square tool. You'll just go ahead and.
Do you want me to give you some dimensions?
Yes, that would be great.
I got it here. Of what? Front face, side, which one?
Let's start with the cross section first.
Okay. 3/4 of an inch.
Okay. Now, since I know that we're dealing with a square cross section, y'all, meaning if you were to slice the part in half, you would see the cross section of it. So that's the dimension there. Knowing that we're dealing with a square cross section, rather than typing a dimension line to make the square, I'll use one of my constraints. So I'll say equal. So I want this curve to equal the length of that curve. So now I don't have to maintain a bunch of dimensions. I can just maintain one. So if I change this to 1, now I have a square, and it's always going to update and be a square. So it's sort of the basic principle of parametric design. You have one parameter driving another, and it makes it easier for you to create different iterations, adjust for manufacturing, that sort of thing. If we were doing this in AutoCAD back in '93, we would have to redraw both lines. So parametric design is very powerful, especially once you get into the actual product development cycle, when you have to iterate and test and iterate, and you have to make changes. You know you're going to make changes along the way as you discover different problems. Being able to adapt like this is very important. So it's an important concept to kind of drive home. All right, now that we have a sketch, we define the cross section on this plane. We can actually create some 3D geometry using a very basic and ancient command called extrude. What this does is pulls out the geometry. Whatever cross section you have drawn, it'll use the plane that you have to define the direction, and it'll extrude it out.
1 3/4. 1.75.
what did I do? Typed in the wrong.
It's not that big.
No. All right. So can you hold up the part to the screen, Monica, please? I want to see what else we got going on.
Oh, like this?
Okay, and on both ends it is the same?
Yeah.
Okay. So that's another thing to keep in mind. Symmetry is something that is really important to keep in mind of. Not only is it one of the elements of design, but you can quickly leverage that in a 3D CAD environment because the computer knows how to make copies pretty easy. So what I'm going to do is actually go back. I'm going to right click down here in this timeline. I'm going to edit the feature. And I'm going to say 1.75 divided by 2. So I'm using a formula to define the length. And that means I'm only drawing the top half of this cube or prism. And you'll see why later on.
And
So,
then what else do you need?
yeah, we're going to need one of the dimensions from the very end on the top. You can give me the width of the channel or the width of each smaller cube that is extruded out. Either one will suffice.
It's 1 centimeter, I guess.
Another important thing for y'all to keep in mind is stay with one specific unit of measurements. We have to go back and forth between metric and imperial all the time, and it's difficult.
Just very bad at 1, 2, 3, 4, 5, 6, 8.
All right.
6/16.
6/16. All right. So actually, Monica, you brought up another good point. This isn't difficult to manage in CAD. Sorry, y'all. So what I'm going to do for my next sketch is I'm going to select the face on this box that we extruded, and I'm going to sketch on that. So rather than sketch all the way down here, I want to interact with the top of the cube. So I'm going to sketch on the top of the cube. So now this origin point appears here. I know that I'm sketching on this face of the cube there. And I'm going to sketch out another rectangle. Oh, sorry, let me go normal to that view, kind of orient the camera.
The 2 lines are already black because they are kind of like constrained with that same.
Correct. They're already constrained, so they're going to line up to this point and go horizontal and vertical. So they're already defined. Now the ends of them are not. That's why these two are blue. So we're going to define the other lengths right now. So if I go to the dimension, and even though we are in inches, in most CAD packages, you can type in a suffix at the end. So if you're going to use centimeters, the software will automatically do a conversion for you. So if this was 1 centimeter, you just type in 1 cm, and there you go. Now, I don't think that it is 1 cm because I know that we have a groove, and I can see right here we're crossing over the origin point. So I think we're going to go with your other dimension of, what was it, Monica? It was 8/16 or
8, 1, 2, 3, 4, 5.
6/16.
6/16.
Quarter of an inch close enough?
Yeah. I think it's too small, quarter of an inch.
Okay, we'll stick with 6/16.
Yeah.
I'm going to reduce that a little bit just to make sure we get a good sized cube in there.
5/16.
The grooves. Yeah.
Yeah. Cool.
So there you go. That's product development process right there. We're negotiating different dimensions, making sure it's going to work for the process. Now, I could have approached this from a couple of different ways. We could have measured the depth of that groove and extruded another set of cubes up from there. But being that we boxed everything in, which is the appropriate method, meaning that Monica gave me the overall dimensions and I made a cube from that. So now I've defined the space that this product needs to live in. It's within this box. These are my overall dimensions. Now I'm going to go back and use a subtractive method to cut into the part and create the negative space that we need. So I'll go and edit this sketch. And if you have any more specific questions, if I'm kind of going over your head, feel free to stop me and ask questions. I'm not sure.
They were
But
asking if the software was completely free or they were like $60 per month or something like that.
no, yeah, that's the great thing. That's why I chose these software. Both the softwares I'm talking about today, they're completely free. I've used them for professional use. The only rule that Autodesk has with Fusion 360 is if your business generates more than $100,000 a year, then they want you to subscribe. But outside of that, you're completely free to use it. You have every feature. There's a couple of high-end features like mechanical stress analysis and the generative design video that you showed them. Those you have to pay credits for. And some of the high-end like rendering capabilities, but their local render is pretty good. I mean, you all saw the chandelier. It wasn't like high-end production level, but it was pretty good rendering for free.
Yeah.
So I've been very happy with it. I mean, I've definitely complained about Fusion 360 over the years. I've been using it for quite some time. It's still sort of in its infancy. It hadn't been around that long, but the simple fact that it's free and they give you access to all the tools, no one can really compete with that. Back in the early days, everyone focused on Rhino 3D because it gave you the most tools for the least amount of money. But yeah, with free, it's kind of hard to compete. So.
And can you explain, not now, but before you leave, can you explain them more about what do you think the future of the design will be, or the
Absolutely.
Okay,
sure. We can get into the weeds with that. So what I'm going to do is mirror this curve since there's 4 of them. So I selected the curves that I want to mirror, and then I selected the mirror line being this axis right here. And then I will run that command again because there's 4 of them. And use a different axis, mirror them over there. So now I have a bunch of different shapes. And if you'll notice right here, when I hover over these dark gray spots, they kind of highlight on their own. If I try and hover over this middle plus sign, it doesn't highlight by itself. It highlights everything, you see? That tells me that there's not a closed shape. So if you look closely here, there's a bold line on this side and a bold line on this side, but there's no bold line going from here to here. And that means that the shape isn't closed completely. I do need to have a line. So what we're seeing right there is the outline of the surface. If you go in 3D, you can see there's no line from here to here. That's because I didn't draw that. All I drew was a square right here. So visually, it looked like there was a line there, but there's no information for the software to use right there right now. So what we can do is we can go and draw lines in between those. That would be a valid approach, right? And we could just eventually close this off. Or a much faster approach would be to leverage parametric design and say, we already have the lines there, right? These edges of the surface are aligned. So we're going to go ahead and project them. So I click this. Sorry, I'm using the hotkey P for project. If you get into CAD, you'll quickly learn the importance of hotkeys. So P for project, and I click the whole face. And so now I have these lines here. They're purple in color to let you know that they're projected, but the software understands how to use them as actual lines. So if I wanted to just select this, this now selects as its own shape. And I'll show you why that's important in just a second. So again, we're going to use the extrude command. I'll click this plus symbol. And what's cool about the software today is they're getting more and more intuitive with every version. So being that I'm extruding into geometry that already exists in the viewport, the software recognizes that and says, hey, it doesn't make sense for you to add this because this is already a solid cube. I'm going to go ahead and guess that you want to cut this. So it's defaulting to cut. You can join, make a new body, or get an intersection. They all yield different results. So if I did intersection, wherever this plus symbol would intersect the cube, you would get that result. I can show a different example later on. This doesn't really make much sense to do that now. Join would obviously just make more of a cube. So we're going to use cut. And built into the extrude tool, they have the taper angle It's otherwise known as draft if you're dealing with molding and casting operations. The reason this is important is imagine this if this were a molded piece, meaning you would have a cavity that would be hollow, right? That's in the shape of this cube. And if you were to inject molten plastic in there, you would eventually want to pull the mold apart in two pieces or multiple pieces, depending on how you engineer it. But you want to pull the mold apart and extract your piece. Well, if there is an angle, let's say I put a negative draft on this.
Oh.
Wait, that didn't. Hold on, sorry guys. Okay, there's a positive for this one. So with this, they would consider this a negative draft, meaning that if the mold fit inside this negative space right here, and you injected it with molten plastic, you wouldn't be able to pull this up apart. It would be locked in because the taper is going the wrong direction. So that's a really important feature for this extrude command. So I'm going and set this to 5 degrees. Even though I typed in a negative value there, that has to do with direction of the surface. It's actually considered a positive draft. But you'll notice it kept these little fins on the side. We don't really want that. That's because it applied this draft angle to the entire shape of the cutter. So from this outer edge, it applied it inward, which isn't really the shape that we want. We want this to be completely hollow through the end. So sometimes these shortcut commands don't work and you have to do what's known as a workaround. Easy enough. I'll go ahead and set this to 0. So now we have the overall shape that we want. We just don't have the draft that we want. So there's an actual tool in here called draft. And what I say is you give it a reference plane. Think of this sort of like a hinge for a door. And then we select the faces that we want to draft. So now we can define a draft as needed. And but we still maintain the cut all the way through. So it's just a little more controlled method of achieving the end result. Okay. So now we can talk about fillets. It's worth discussing them. They are part of the process overall. So for this, I'm going to go ahead and use the chamfer command on the outside. We necessarily wouldn't have to use that. I just wanted to show y'all how this works. And usually you would pick a series of edges or one edge, depending on whatever the case was. And you would define a distance, right? And if you look right here, it says equal distance. You can actually define this with 2 different distances, meaning your chamfer doesn't have to be symmetrical. So you can have more chamfer here and less here, depending on what the design needs are. Or you can define it by an angle. There's distance and an angle. So you say, I want you to go this far in, and then from that point, I want you to come out at a specific angle if you're trying to match some other aspect of the design.
That's a cool design right there.
This is the iterative process and work, right? This is sometimes how product development works. Along the way, you're trying to solve problems, and you might generate a completely unique design in and of itself. So it can be very rewarding, even from a design aspect as you go. So I'll go ahead and leave those chamfers in there just for reference sake later on. Another concern you might have is in creating your pieces. So the real power of 3D modeling and CAD geometry today is manufacturing, right? Being able to turn it into a physical product. So if you wanted to have a mold to inject hot plastic into, then you would need a machine to create the part. One of the oldest and most trusted methods is a milling machine or a subtractive device where they go and start with metal stock and they cut out the cavity of the shape that you want to create. But something we have to keep in mind is how those machines operate. So a milling machine is essentially a drill bit that cuts on all sides. and they have different types of shapes for the drill bit or the end mill. But a lot of times what they use is called a ball nose end mill, which basically has a radius at the bottom of the cutter. So what we have to do is create things that don't have sharp corners on the internal edges, because the milling machine can't reproduce that. So a lot of times we have to go in there and add what they call fillets. So I'll go ahead and identify all of my inside corners. And we'll drag this up, and usually they'll, uh-oh, I forgot one. So I can just hit this plus sign. Again, parametric design is very powerful. You can, if you forgot to misclick, or you misclicked and you forgot something, you can always add in extra inputs, and you don't have to rerun the entire command. So, so we'll have to add fillets in there and, you know, define a specific radius. This value will be determined by whatever end mill your machine shop is going to use, or your client is going to use. It's not some arbitrary thing. Your tool will define what the minimum radius is here. So now we have a radius that's going to mimic what the actual CNC milling machine is capable of producing. Now with 3D printers today, like what Ms. Elbjorn had printed for the toy, this isn't really a consideration. 3D printing is an additive process, obviously. So you don't have to worry about what machining bit can cut what. We can have sharp corners and eliminate all of that. We can add any shape we want. The 3D printer is capable of creating that down to a certain resolution. Another way you can create fillets is by selecting an entire face. So if there's a whole region that you need fillets on, and it knows how to interpret those edges and create fillets right off the bat.
Very cool.
Right, so now we need to create a hole down the middle, I believe, right? There's a string going through it.
Yeah.
Okay. So,
but will you first I was gonna say, like, if the hole is gonna go all the way through, that's just half of the piece.
Yes.
So I'll wait until, I guess, you explain how are you gonna do it.
Okay.
So the hole is just, it touches the four corners.
Okay. So what I'll do is, let's see. There's a couple of ways we can do this. The longhand way, if you were doing a very specific hole that was a unique shape, like let's say we grabbed the spline tool, and let's say it wasn't a cylindrical hole. You wanted to create this really amorphic shape and cut that through. You could go through and sketch this and extrude it. And let's say I knew I wanted to cut all the way through. I wouldn't define it by distance. I would say through all, and I'd say cut. I can see by this arrow, it's going the wrong direction. I want it to go down, it's going up. So I'll flip the direction here. So now it's going to cut a hole all the way through. All right.
Yeah.
So let's say I submit this and design comes back and said, no, David, that's completely wrong. We wanted a cylindrical hole through there. You drew this weird amorphic shape, and that's wrong. So what I can do is go ahead and suppress this feature. So I don't have to delete anything. I don't have to redo anything. I can just suppress it. Say, all right, I'm not going to use that. It's a cool design. You know, it's a cool option. Design liked it. They said we might use this for another product later on down the road, but for what we're going forward with today, that's not what we're going to use. So I'll go ahead and suppress this. And there's, with most CAD software packages, something as standardized as a hole. They usually have a tool for that because we use bolts and screws and fasteners for that. So they usually have a specialized tool that's designed strictly to make cylindrical holes of various types. So this has a hole tool. I hesitate to use the term hole wizard because that's something for SolidWorks is another software, but the idea and the principle is the same. So first it wants you to do is select the placement. So it wants you to select the face and then align it with some point on the model. So you can say, all right, I want it locked in the center there. And then it gives you an interface, right? So you can have a reference for various aspects of the hole, or you can just simply define it by a distance. So you say cut through all. So you can kind of see there, it's cutting through everything. What hole type do we want? What size do we want? So this we can tie as what, 5/16, 3/16. Nope, that's too big.
1/8.
Thank you. So let's say 1/8. All right. We're cutting through everything. There are different options. We can thread the hole. We can have a tapered hole, clearance hole, all different methods we can use for that. If we look at the top, we can say, I want to have a counter bore, right? So if you wanted to have like a Allen head key that needed the head to fit in flush there, if you're going to bolt it together, or if you had like a wood screw and you're going to screw something together, you could have an offset for that as well, right?
Cool.
Or you just have a straight, we're going all the way through. So go ahead and take that back in. Okay. Now you can see that we have an error right here. So this fillet isn't working with the hole cut, right? So what we could do is go back and edit that. Yeah, that was a little bit too big of a fillet. All right, so we're going to reduce that one to 1/64. I'll say this is 1/64. Okay, now our hole is good. We have a nice solid part. There's no overhanging faces. This is good.
Cool.
So, Monica, now to your point, this is only half the part, right?
Right.
Now, imagine all of these commands. You know, I ran an extrude to cut the grooves. I did all these fillets, chamfer the sides, all of these things. If I had drawn this part to full dimension, I would have to mimic those commands twice and draw them all over here, right? Or we can run a mirror command, select bodies, select the mirror plane,
Oh.
so you just cut the amount of clicks you did in half, right? So you, well, not in half, but you saved yourself a lot of time and effort, and not only time and effort of clicks, but time and effort for managing the data that you have to put into these things, right? The radius for your fillet, does the hole work for this? You know, does the chamfer work there? If you had to do that, you'd have to manage twice as many numbers as well, which can be a little overwhelming and make your job less fun. Like no one wants to do math and type numbers 24/7. You want to get into the design and the CAD and the creation of it as well. So the more we can do to manage less of that,
Okay.
the better our
What
job is.
about if now you want to put like other piece?
Oh, you mean like mimic what you have there?
Yeah.
Okay. Now we're getting into what we would consider, let me make sure I combine these two. I'm not sure that they were joined. Yeah, so I just want to clarify that. See this dark line here? This let me know that these were mirrored, but they were two separate bodies. So I used the combine feature to join them together, and now it makes one solid body. So now the computer understands this is one unit.
One.
Yep. So
Okay.
now we can save this as cube part. Okay. And we can start to make an assembly of multiple parts. So different softwares deal with this environment differently. But the basic idea is that once you create this part, you can create multiple instances or copies of this into a larger assembly. This, they call it components that live in a part file. SolidWorks will call it components that live in an assembly file. Rhino will call it block instances. Like I said, they all have their own language, but you're sort of learning the fundamentals of CAD the same way you learn the fundamentals of design and hand skills. There's certain fundamentals of CAD that you can learn along the way that'll translate from one CAD package to the other. So again, don't focus so much on the tools and the features, focus on the fundamentals of creating geometry, different types of geometry, how all that works. The vocabulary might change, but you'll learn enough as we go. So now that I have the part saved, what I can do is start to drag this part into a new file. Oh, had an error, sorry.
So what you're saying is that a lot of the softwares share the same tools? Because I was explaining them that there are kind of like different types of modeling, like mesh modeling, surface modeling, and solid modeling. So this will be a solid modeling, correct?
Yes, that's a good point. What we're building right now is a solid model, but some of the principles for like what you're talking about, we're creating a part and we're copying it again and again as components for a larger assembly of parts. That process sort of translates to all the 3D software types. So if you're a mesh modeler, if you're a surface modeler, if you're a solids modeler, this idea of creating a component and then making copies of it that you can change, like maybe it's a different scale every time you use it, or but it's all referencing this one part. So you don't like change 50 of the same component. You just change a one, and it's like referencing all of its data from that. That concept or that fundamental process is relevant for mesh modeling, surface modeling. It's all the same. You're going to create a part that will be managed one time, and then you can copy that part multiple times in there. So I have an assembly already made. I'll go ahead and reference this just to save some time. But basically the way that this works is we created a pattern along a curve. So I drew this 3D sketch, and some softwares have better tools than others in terms of defining components and how they link together. This one's fairly rudimentary. You have to do a lot of manual effort to make sure everything lines up. But yeah, that's all we did. We created this one part. I ran this command. I picked the curve that I drew, and now it's just copying that. There's some options in here that I selected. So it's following the path, and you can change that to identical. So, it's keeping the orientation of the object as it was originally, and then it's just locating it along that path. Or you can select the option to follow the path. So it's actually kind of treated like a roller coaster, right? It's just kind of riding around and following the tracks as it goes in all axes. So it'll twist, roll, pitch, and yaw. It's going to X, Y, Z. It's going to interact with all those axes to define how that curve functions and behaves. So yeah, that's kind of how that part is made. Did that really answer your question there, Monica?
Yeah.
Okay. Now we can move into surface modeling. So surface modeling is a little bit different than solid modeling. Solids are used to using, 2D sketches that define fairly predictable shapes. You can make something look very complex with solid modeling. Actually, let me show you an example of that real quick. I'm going to fly through this. I'm not going to really explain a whole lot, but I'm going to try and make something that's at least appears complex.
Wow.
Any questions so far? It's kind of boring just to watch someone click.
Mm.
Let's see, we'll put some fins on here.
It's crazy all the things that you could build. Basically everything.
Yeah, it all happens fairly quick, you know. Oh, sorry. Do it before they fill it. Not putting anyone to sleep yet?
Uh-huh. No, we still got the same participants that we start with.
All right, cool. Anyway, so you kind of get the idea, right? This isn't an extremely simplified part. We got some fairly complex things going on here. Right? But that's kind of some weird little camera radiator thing. This was all created from fairly basic geometry, right? We didn't do any sort of amorphic shaping really. And we have some compound curvature here. It kind of doesn't look like polygon modeling. It's complex, but you're not going to see these types of shapes on like an Audi or a Jaguar, right? They're going to really define what they want the shape to look like, and that's where surface modeling comes in. Now, I don't want you to confuse one software package with a certain type of modeling. Most software packages nowadays, well, I say most, a lot of them have solid and surface modeling in the same package. So, for instance, SolidWorks, system by Dassault, has been around for a long time for mechanical engineers. They're primarily known as a solid modeling software, but they also have surface modeling tools within it. The same is true with Fusion. So we're going to start a new document, and I'm going to start creating some surfaces. The rules for surface creation are a little bit different. The only thing I don't like about the interface of Fusion is like if you go into surface tools, they don't have your sketch bar in there. So you have to stay in solid to get your create a sketch icon there. You can customize all this. There's thousands of tutorials for Fusion. I'm not going to waste your time with all that. But so we're going to create some sketches now. Being that we're going for more of these stylized shapes, I'm going to use a stylized curve generator. I'm not designing something mechanical. I want it a little more fluid. So I'm gonna use what they call a spline. Just it's sort of like a curve or a line that has predefined curvature along with it. So there's different types of splines. Um, there's a fit point spline or interpolate spline, and then there's a control point spline. Um, Again, I'm not going to go into a whole lot of detail about the difference between those. There's plenty of videos, and as you work, you'll quickly learn which ones are better for you. I'm just going to show you the difference in how they look right now. So they're somewhat defined differently, right? The fit spline or another software's interpolate curves are defined by these handles. This is probably something if you're ever familiar with like some of the tools in Photoshop and certainly Illustrator, this is the type of control handles they use. You'll be very familiar with that. You have the degree of tangency for that inflection point and then the angle at which it's going to operate. Control point curves they're sort of defined more akin to like a subdivision modeler. It's really kind of cool that you have these really basic polygon curves or polyline curves, and they're actually defining the curvature of the line itself. So different workflows, you just kind of decide which one works for you. I'm going to delete those. I'm not actually going to use them. Sorry. So first things first, I'm going to decide what I want the shape to look like. Let's say I'm going to go with the front fender of the next best car, right? Mm. So first thing I'm going to do is decide what is it going to look like from the top view, right? We're getting back to the fundamentals. Even your most complex design will come back from the fundamentals. So we're going to say from the top view, what is it going to look like? That's what I'm drawing right now. Please don't actually grade me on this. I have nothing in mind. I'm just kind of going along. Oh, sorry. I get confused with the commands. And SolidWorks is a totally different key for ending that command. So click the check mark there. And then we'll draw a straight line just to define the end right here. Okay, so now we have a shape defined from the front. From the top, sorry, from the top. Now we're going to go and finish that sketch. We're out of that sketch. And we're going to define what it looks like from the side. So in order to do that, I'm going to need some reference points. So this is where those technical drafting skills come into play, understanding the fundamentals of those and how they work. I know that I want to define the shape from the side view, but I need my endpoints to match, right? I want to make sure I create this in the same end-to-end space. So I'll use the hotkey P to project this curve onto the plane that I'm actually sketching on. So now I know these are my constraints. I have to fit whatever shape I come up with between these 2 points. But I don't want to actually use this curve, so I'm going to do what they call create a construction curve. It's going to create a dotted line. That means that it's there for reference use only. You won't be able to create a shape or use it to generate a surface, so that this is sort of a way to ensure that you can have reference lines that won't get in the way of what you create. So if ever you see a dotted line and you can't create a surface, that's why. Or if you're creating a surface with a line that you don't want to, make it a construction line. It'll kind of keep it out of the way. And now we're going to sketch the shape that we want. You'll notice as I move these control points around, this shape is still confined, right? They're not moving in 3D space. They're always flat. And I can't take this control point and move it out side to side, right? It's always going to stay on that plane. It's because the sketch is on that plane. So we're still dealing with two-dimensional sketches. Okay, I'll go ahead and finish that sketch. And I'm going to go back to my original sketch, and I just thought of a cool feature to show y'all that I think would help drive the point home. So you see, I have a yellow icon here. This is generating an error. I deleted the line that it was referencing. Sorry, hold on, y'all. Kids are up from that time, so. I lost these reference points here. So what I need to do is reproject the reference curve since I deleted the previous one. So we're good now. Let's see. Trying to get something kind of unique going here. So I know what I want it to look from the side. I know it looks from the top, but I need to generate sort of like a three-dimensional curve, right? But that's not the easiest thing to do. So what you can do is employ your fundamentals from drafting and say, you know what? If my two curves intersected, they would create a curve in 3D space. So we can actually use that tool right now. So what we can do is extrude the surface. So this will let you pick just a singular line. Whereas when we extruded in the solid modeler, we had to have an enclosed shape. Remember, the plus symbol wouldn't work until we drew those lines. Well, the surfaces are different. They know how to take just a surface plane and extrude that out. They don't need it to be a solid. So you have a little more options. And then we can extrude this right there. Okay. And now we can combine these two. Oh, no, I just lied. Hold on. Trim, there we go. So the trim tool, and we can trim this surface out. Okay. And we can run that command again. And we'll trim. Trim tool. Okay. So now we can go to sketch. Repeat. Sorry. So now we have this 3D edge that we can use to generate other geometry if we wanted to. See how it's kind of rolling through all the different axes and planes. So if we wanted to create another version or iteration of that, we can start to define other curves as well. Let's say that maybe we want this, we like this curve here, but we obviously don't want it to come straight up, right? This doesn't really look right. So what we can do is go ahead and sketch it from the front view as well. The problem with sketching it from the front view is you're only dealing with a certain cross section at any given time. So that might not yield the exact results that you want, but you can still define it as you go. So we're starting to get into a 3D sketch space of sorts. Sorry, this. Is everyone following me so far? Am I kind of going over your head?
Yeah.
Yeah, I am. I'm going over your head, or we're sticking with it?
I still see the same people connected.
Like I said, guys, y'all feel free to ask questions as we go. Sorry, hold on. Sorry, obviously, nothing ever goes as planned when you're doing a demo, right? Come on.
So cute.
Surfaces.
Mhm. Oh.
So you can start to create a little more complexity there. You can also, you don't have to be restricted to just one plane. So I can create an offset plane right here. So now I can sketch on this plane, right? And I can project these curves, right? I'll set them all to construction because I don't want to build with any of those. I just want them as reference points. And I can start to generate a cross-section curve.
And you're still able to combine solid modeling with surface modeling?
Yes, you can. It's a little trickier to get right, but you absolutely can, yes. Basically, with any solid modeler, you have to, if you're going to employ surfaces, you have to make them solid by default. Surface modeling gives you a lot of freedom, like we're seeing right now. You can really get some of these unique shapes, but it doesn't necessarily mean that you're making a solid surface. It might join correctly, it might look solid, but there's, like, on a mathematical microscopic level, there's little inconsistencies in your surfaces sometimes, and that won't give you a really good result. It won't give you what you're expecting. And you have to go through a couple of extra processes to make sure that they are in fact correct. And sorry. You have to go through a process of like stitching or knitting them together to close up all of those edges. Okay. So this is a really common surface creation tool called Sweep. Essentially what this does is it defines a cross section, like I talked about with the cube earlier. We use a square. In this case, we're going to use these open-ended arcs, or these splines, sorry, as our cross section. And then we're going to apply a rail. So the first thing it asks for is a profile, which is your cross section. And then it wants a path. What am I going to follow? Sorry, we don't want to change selections.
Connor says that it looks like the head of a snake.
Oh, that's cool. Yeah, we're designing a fender for a cobra. It's a king cobra. There you go. Nice.
Wow.
Okay, so we picked a path, right? And we picked a cross section, and it created this shape. And albeit a cool shape, right? It doesn't really follow what we had kind of boxed in for our form. You see? We had ours tapering off to a point. And this one is just kind of continuing on. So what we're going to do is actually change this command. And we're going to use a path and a guide rail. So the way this works is
That's pretty cool.
we're going to select two path rails. So we're going to select the first one and then select the second one. Oh, wait, sorry. Okay. So we're going to create one half of it right there. So now you can see we're really getting into this stylized approach, right? We have a lot of control over the surface quality. We're not relying on fillets or chamfers. We're really allowing the splines and taking a more artistic approach towards creating geometry. So we just go ahead and repeat that command for the opposite side. So go ahead and create the sweep. Select the profile. Oh, sorry, we're going to path and a guide rail. So select the profile, select the path, and select the guide rail. There. Flip the direction. There we go. This looks a little better, right? So we'll go ahead and do the same thing over here. Let's see, this is sketch. So yeah, as we're going, it's hiding the sketches as we use them, just to kind of keep them out of our way. Not necessarily what you want all the time, but I'm gonna go ahead and edit this sketch real quick, just to make sure we line up with some of our edges. And it's not letting me. Okay, this one's locked on the constraint there. I'm going to delete that constraint.
Yeah, like they were saying, like this looks like a cobra. Surfaces will give you more organic or more natural shape compared to the solids that it looks like square, or it'll be more hard to create a model that will look like this.
Correct. It's a very good point. Oh my gosh, it's 3:30 already? Sorry, y'all. Taking a lot longer than I thought.
Thank you for taking the time for explaining all this. It'll be
Of course. I hope someone finds it useful.
for them. Can you imagine if they start learning this by their age? I started learning this, I don't know, when I'm in my 10 years ago. Like I don't want to say my age, but.
No, that's another good point. If this at all interests you, again, that's why I wanted to choose free software to go over, because they're, even when I was in college, YouTube wasn't around yet. There's so many instructional videos on YouTube, and you could get all the training that you want for free software for free. So essentially, you can have associate level knowledge of, equivalent to associate degree for free if you just start studying now. If you enjoy it this much, and you're not, you have the time and the resources to invest in it, that you won't regret it. I mean, CAD is just a tool that people are going to use forever. It's not going away. It's only going to become more and more part of what we do.
It's getting better.
Yep. It's a tool that's going to be here to stay. So just any version of it that you can learn any CAD, it'll transfer some way, some shape, some form, or it'll get you a job that'll let you train on other software. So pick a CAD package, learn it inside and out. Free software is great. I use it all the time. There's just a lot of resources out there for you for free. You can get a lot of education.
Along with statistics, I know statistic and probability sounds really boring, but really everything, it's combined together.
Oh, absolutely. Like that video you shared. Sorry, real quick, just going to interject. What I'm doing right now is a subdivision modeling. So I'm gonna keep doing this while we chat. Y'all can ask questions as we go, but I'm just gonna kind of show you how this is sort of this isn't quite ZBrush. If any of you have heard of ZBrush, this is similar because you're dealing with something that's sort of like a piece of clay, right? You're actively sculpting. This doesn't really play well with parametric design. In some applications, it does. Um, but I just kind of want to show you what sub-D modeling is all about. Your subdivision modeling. So as you create more and more faces, it's subdividing this out. And actually behind the scenes, there's actually a polygon that you're seeing or you're not seeing that's sort of defining this. It's very akin to the control point curve that I showed you on the other project. Let's see if I can find that. So see these control point curves right here? They have these straight lines are actually defining a curvature, right? Well, the same thing is happening with this. This is T-splines software. This is subdivision modeling. So every curvature in 3D that you're think of these straight lines creating this boxy mesh that goes around it. That's actually defining this. But they have a special math algorithm that's smoothing all of this out and making it look nice and pretty for us to play with. But yeah, so sorry, what were we talking about, Monica? You're talking about yeah, statistics and learning all of these things. Yeah, there's so much training out there for free.
And can you say really quick about how do you think designing the future will be?
It can go a couple of different directions, but ultimately design is going to be more data driven. So statistics, I think, are going to play a more important role in design in the future because you can statistically analyze a problem and then have AI generate possibilities using generative design, something like that we're seeing in the video there. But I mean, virtually everything that we do, if you're not a standalone freelance artist just creating actual art, if you're in any sort of product development, you're operating within some form of statistics, whether it's from your marketing team or your engineering team or something. There's some level of math and coherent understanding of a problem that you're trying to solve, whether it's getting relevant product to market or solving a need that's not out there yet. You're referencing statistics to kind of guide you where to go. So I think that's always going to be relevant. And in the future, it's really going to be more about sort of like what I was talking about with the conceptualizing ideas. So we have, you know, your designers sitting there doing all these sketches and thumbnails and things like that. In the future, I think it would be, you still have your design team, but rather than manually going through those ideations, you could quickly take 20 ideations from a conceptual designer and feed that information into a computer, or take, you know, 50 setups for a mechanical bracket or something like that. Define some sort of problem that you're trying to solve, and you could have the computer using generative design create 200 more concepts, right? And they would do this, the computer would keep working throughout the night, right? It's not going to stop. It's a computer. So while everyone's going to bed, sleeping and having a good night's rest, now we come back the next day and the conceptual designer's 20 iterations are now turned into 200 options. Now, maybe 80% of that is garbage. We're not going to use it. But that 20% we got for free. You know, now we have that many ideas that we can leverage further that we might not have thought of on our own because we're sort of thinking within the confines of traditional mindset. Right. Or B, it's just the amount of time that it would take us to get there. We would have to go through 180 iterations to get to that last 20. Well, then now we don't have to do that. So the computer can do that for us, and it can leverage our ideas even farther. And we can get more bang for our buck that way. So I think it's definitely in its infancy right now. It's sort of like the steam locomotive versus the horse when that first came out. You know, the steam locomotive was far inferior to the horse. The horse was faster, it's more reliable. There was a system in place. They understood it. But as time went on, people realized that, yeah, the steam locomotive might break, but we can order parts to fix it. You know, horse breaks its leg. You can't order a new leg for the horse. It's kind of a problem. Or the horse gets tired and needs to rest. No, as long as you're feeding coal into the steam locomotive, it's going to keep going. You know, the problem was refining the technology to produce steam, refining the components used to build it, refining the infrastructure, building an infrastructure for the tracks and the train to go on. All of this is sort of a huge metaphor for data, statistics, and generative design in the future, and how AI is going to help leverage that more and more.
Right. As they were saying, designers are afraid. What about the designs that they didn't think of?
Exactly. You don't have to worry about that anymore. And it's not costing you anything except, the cost of whatever software it is that's going to provide it, and the electricity you use is far cheaper than trying to hire 10 more conceptual designers. It's not really a feasible option.
The perfect design.
Exactly. So
that looks pretty cool and easy.
Yeah, T-spline subdivision modeling is a lot of fun. You just kind of go with it, and yeah, it's a blast. You can keep adding edges. You can add both sides. So as you keep adding edges and faces.
So this will be like a mesh modeling type of thing?
No, this is sub D. I don't have, actually, I can get into Blender a little bit. So mesh modeling is a little more different. This is somewhat similar because you're sort of, it's more amorphic, it's more organic, and not only the actual result, but the process itself. It's not very mechanical. We're not defining angles and dimensions. We're just loosely defining a shape, right? But with mesh modeling, they're actually using polygons and triangles to define it. So your geometry, the math behind it, the capabilities behind it are a lot different than that. What's special about this, why they call it T-splines, is that it's a spline that understands how to handle these intersections with a T and keep everything smooth. So if you're trying to do this in a surface modeler, you would have to really, it's possible, we could do it, but you really have to understand your geometry very well in order to create that by hand. So having the technology and the math behind subdivision modelers to be able to handle these intersections, see this? We have 5 edges coming to one point. To keep this smooth and tangent throughout all of our adjustments would be very difficult to do by hand. So this type of tool handles that really well. So it's still creating surfaces and faces. These aren't meshes, but they behave similarly to what you'd expect in a mesh modeler, meaning it's more sculptural in its approach. There's a few other commands that I could go through from the solid modeler, like revolve and things like that. If anyone's curious, Monica, I'd be happy to go through that again some other time. I don't want to burn up everyone's afternoon. I think we've already been here for
that'll be awesome.
Yeah, happy to help anyone. If you have any questions CAD related, you want to go more in depth with this, happy to. I just want to quickly touch on Blender. This kind of speaks back to my days in college when I was an animation major. I was trained in Maya. Blender is definitely not Maya. Blender is not industry standard. Animation houses have used it, but it's not an industry standard. I think it's getting there more and more. There's a recent update that it just came out with that makes it way more friendly to use. But this does have a mesh modeler in it. So we're going to go ahead and add a mesh. Let's see. I'm going to add a torus because there's a tutorial out there for this that's actually it's actually a lot of fun because you end up creating a donut. It's just kind of fun. So I'm not going to create a donut today. I'm going to let you do the tutorial. So let's see. So what this is doing is oh, sorry. All right. So we just subdivided this mesh. It started out really rough. We subdivided it. And what that means is similar to the subdivision tools and the sub-D modeler for T-splines, it just increases the resolution. Think of it that way. You're increasing the resolution to get more refined sculpting. But basically, it's just sort of like 3D Photoshop, right? So they have a series of brushes here. And then you have the intensity, right? The strength, the radius, you know. Again, I'm not going to go into a whole lot of details with this, but you can just drag on this and kind of sculpt and build up material. Different brushes are going to give you different results. Let's see, rotate around here. Looks like I got some kind of symmetry on, unless it was a back face. Yeah, there's symmetry on somewhere. Let's see, we have some cut tools.
Wow, that's pretty cool.
Yeah, I think my resolution might be a little high here. But what's cool about this is you can actually move these as well. So if you want to get some rough edits, so this actually illustrates it really well. I totally forgot about this. They call this like a proxy mesh, but this is actually sort of behaving similar to T-Spline's subdivision modeler, which is kind of unique to see both in a mesh and this. But you have this polygon defining your mesh. A similar thing is going on. So you see you have your smooth edges, but you have these polygons out here. These are like the control point curves I was telling you about. They're defining the curvature of the mesh. So if I wanted to make some really quick edits on my mesh and I didn't want to have to sculpt them in, I could quickly adjust this polygon and really move like a massive amount of area and quickly define a different shape, if that makes any sense. Right. So now when I go back to my sculpting mode, I have this really cool shape that I can work with now and totally turn into some, like, I don't know, a buckle for a kilt or something. I don't know, some cool thing.
A cobra.
Yeah, cobra. Maybe we could turn into cobra. I don't know. Not enough time, but another time maybe. So yeah, hopefully this kind of answers some of your questions about CAD. This probably wasn't the best organized approach to a crash course, but I just kind of wanted to expose y'all to some of the concepts and kind of speak about, again, the fundamentals, understanding that, technology, the latest CAD software, an awesome PC, it really doesn't matter. It doesn't matter what software you learn. I mean, certain softwares will be more relevant to other industries. VXF and animation definitely have their type of software that they use, but even within every industry, there's multiple softwares that they use. Like ZBrush is another, it's a pay-to-play subscription mesh modeler that's been around forever. You got to pay for that, but understand those concepts would apply because game designers, they use that for character creation, definitely. Conceptual designers use that where Monica and I work in jewelry creation. But we also use Rhino, we use SolidWorks, we use Fusion. It's really just a toolbox. So don't get too focused on any specific tool. Learn a tool, master one. First, master the fundamentals, but then pick a software, hopefully one that's free. Don't waste your money. You can learn a lot of the fundamentals on these free softwares. These are full-blown packages. They don't restrict any functionality. So Blender and Fusion are my recommendations for getting your feet wet and understanding 3D modeling. Please, if you're at all interested in any of those industries that involve 3D modeling, if you're going to be a mechanical engineer, a product designer, industrial designer, even an artist, 3D art, just if you're going to post in a gallery, it's all relevant. So dive into these softwares, ask questions, get on forums, YouTube the heck out of them. There's so much good training on YouTube. I've learned, like in my professional career, I've learned a lot just from YouTube. You really can go a long way, especially if you start now. If it's something that you're interested in, you're passionate about, you can go a long way without spending a lot of money. You don't need any school. If you're just interested in the technical aspect of design and understanding CAD work, if you're going to learn the fundamentals of design, I would strongly recommend going to a school and learning that. But if you're interested in CAD and that sort of thing, start learning now. There's no reason to wait.
True. And later on, everyone will have a 3D printer and they can print their own things. But for now, I have this toy that I wanted to give away to the participants that were here. And I put, guys, all of your names like in little papers, random. So David, pick a number from 1 to 17, and then I'll start picking one name.
Okay. What's the probability of me picking 4?
It will be 117.
Number 4.
Okay, so 1, 2, 3, and 4. This is my 4. Let's see if we got her here. No, I don't think she's here. Should I pick another one? Or should I?
Are you asking me or them?
Everyone. Well, I think we should pick another one.
Well, yeah.
Okay, pick another number.
7.
7. 1, 2, 3, 4, 5, 6, 7. Tatiana. Oh, Tatiana is here.
Is she here?
Yeah.
Awesome.
Okay. Well, Tatiana, I can email or I can mail this to you whenever you give me your address, or we'll figure out how. Cool. Well, thank you so much, David, for your time, and thank you guys for taking your time from your Saturday afternoon. I know you got better plans, but I think this is one of a lifetime that if you really are interested in being a designer, an artist, or something that is related to designing something or to test something, this will be the way to go.
Certainly. So I hope you all enjoyed it. I hope everyone learned something. I can be a little long-winded, so I didn't want to get too thick in the weeds with all the subcommands and technical aspect of the 3D modeling. I just wanted to kind of get y'all to understand that there's options out there for free to start learning now. Take advantage of it if you're going to do this, if you're interested in it. And like I said, y'all let Ms. Elbjorn know, and I would be happy to answer any other questions y'all might have along the way if you're getting into 3D CAD design.
Okay, thank you guys. Bye.
Bye.